So example 1, tips for a delivery person. You can read the description there. What I'm interested in is this data set. So make sure you have this paper out because you're not going to be able to see my data set. You'll need to go to Remote Apps and take care of the Citrix receiver. If you need a refresher on how to do that, there is a video available in your Blackboard course shell. It is under Test 1 content. Okay, so if you go to course content and choose Test 1 content, you will see accessing datasets and Minitab through remote apps. So I'm not going to cover all that today. I'm just going to go ahead and go there. I'm going to open Minitab. I'm going to open Chrome, and I actually already have those open. It takes just a minute. Notice the Chrome I was originally in, I had set a theme on so that my tabs were green. That way I can tell it apart from the Chrome that comes up when you click it in your apps, your remote apps. It comes up gray, so I can tell them apart. I want to be within this Chrome browser when I download stuff. I have also opened Minitab, and you can see here it is blank, but it is opened in remote apps. I'm going to minimize that. And I'm going to first go to StatKey. The data that we're using for the pizza delivery person is not available in these data sets. So I'm going to go to StatKey and modify one of the data sets that they have. I will also maximize this browser so you can see it. We're going to be dealing with one quantitative variable. And now I can see that this is mammal longevity that is graphed here. I don't want that. I want to edit my data. I'm going to clear all of this. So Control A, nope, just delete. Okay. I'm going to put not an identifier for each of these, but I will put a header row. So I set that the way I want it. My header is going to be tips. And then I start entering the data. Each datum goes on one line. And there's all my data. Okay, and there it's graphed. Look at this. We have this one point out here. And when I see that 32 there, and I look at my data on my worksheet, I see I don't have a 32 there. So I'm going to go back to edit data and figure out what happened. There I have an outlier that didn't really exist in the data. I made a mistake in data entry, and that may well happen. So let's see, I have 2.5, 8, 2, 2, 2, 3. I hit that 2 accidentally when I pushed my 3 button on my computer, because look, I had the 1, 2, 3, 4 threes in a row that I'm supposed to have. So that is just an extra stroke. Let's see what this data set looks like now. Okay, there we go. That looks much better. The outlier there is a tip of $8. That looks much more like the data that I was supposed to be entering. So look for things like that in case you've entered some data incorrectly. And I'd rather see this as a histogram today. So here I can play with the number of buckets. That's changing the width of these buckets here, the columns. Here the columns are, and look at this. If you scroll down just a little bit and you scroll over one of the buckets, it tells you down at the lower right there what the lower bound is and the upper bound. So the lower bound of this bar is 4.8 and the upper bound is 6.4. And there were 3 tips that fell in that bucket inside those values. This bucket is from 1.6 or $1.60 and $3.20. And 16 of the tips fell within that range, within that bucket. This one looks a little more normal. Okay. Here the lower bound is 2.7. The upper bound is 4, and 8 of the tips fell in there. You can increase the number of buckets a lot. These are very small buckets. The lower bound for the bucket here is 4.36, and the upper bound is 5.0, so less than $1. And 3 of the tips fell in there. So that's what the buckets do. Okay, so what we were asked for this was not to play with the buckets, though. It was to find the mean, which our technology has done for us, 3.042, and to find the standard deviation, 1.750. So you can play with these buckets all day, but as soon as you get your data entered and hit OK, it's going to give you the values. So let's see if we can copy this and just paste it onto our page. So copy. And I'm going to pull the page onto the screen here. And down here, I'm going to say this came from StatKey. And there it is. Let's minimize this and grab the standard deviation. Highlighting that. Copy. And there. Standard deviation. All right, moving on to the next example. Example 2, percent of body fat in men. The variable body fat in the body fat data set gives the percentage of weight made up of body fat for 100 men. For this example, the mean percent body fat is 18.6 and the standard deviation is 8.0. And the distribution of the body fat values is roughly symmetric and bell-shaped. We're on a computer, so let's check this. Looking for the body fat data set. So here I am still in StatKey. Let's take a look at body fat. Is it on here? Not on there. So I am going to have to go to my data set now. I go back and I'm still in StatKey. So I go back again and here I have data sets. I have gone to the second edition of the data sets because that's our book. And here is the body fat data. I need my Minitab file, MTW. It downloads here at the bottom. And when it's done and I click it, it will open Minitab and will open that distribution. Okay, may take it a moment. There's body fat. Now, we were asked to look to see if this was approximately normal if we're on a computer. So graph, histogram, it's a good way to do it. I'm going to do a simple histogram. Click OK. And my body fat here is in column C1. You can either find it here and double click, or you can just type in C1, enter. And there's a histogram of body fat. It's not perfectly bell-shaped and symmetric, but it's pretty close. So we're going to go with that. Okay, so I'm going to find an interval that is likely to contain roughly 95% of the data values. Well, I've checked it with the graph to see that it is approximately or roughly symmetric and bell-shaped, and it was. But really what I need at this point, since I have these values, is just to use them. Because due to the 95% rule, you know that 95% of the data is located 2 standard deviations below the mean and 2 standard deviations above the mean, or rather it's located between those two values. So first we need to figure out what is 2 times the standard deviation, or 2s. In this case, it is 2 times standard deviation is 8.0. So that equals 16. Our mean percent body fat is 18.6. So 18.6 minus 16 equals 2.6. So that is our lower bound. And 18.6 plus 16 is 34.6. So there we have our lower and upper bound. The interval then, okay, let me put that in red just to make it stand out, will be 2.6, comma, 34.6. That's the interval on our graph that will contain roughly 95% of the data values. That's 2.6 to 34.6. Let's see that on the graph. Where'd my graph go? Let's see, 2.6, about in here, to 34.6. Okay, so here's my graph again, and I've drawn an approximate normal curve here. It should not come down all the way. It should never go, it should never even touch the line if I draw it correctly. Okay, but 2.6 in that area and 34.6, it's approximately 95% of the data falls there. The largest percent body fat of any man in the sample is 40.1, and the smallest is 3.7. Find and interpret the z-score for these values, which is relatively more extreme. Okay, well, when you are figuring out a z-score, your z-score is always going to be your data value minus the mean divided by the standard deviation. So there's our formula for a z-score. For the example that we have before us, we will make the substitutions that we need to. So let's just copy this. I'm going to make it a little bit bigger so you can see it easier. Instead of our x value, we have for this first value, 40.1. We're interested in that. And for both of these, of course, they come from the same data set. Our mean is given above, 18.6, and our standard deviation is 8.0. And when you calculate that, it comes out to 2.69. Let's figure out the z-score now for the smaller of the body fat percentages. The smallest was 3.7. Everything else stays the same. The data we're interested in minus the mean divided by 8, which is the standard deviation. And in this case, we're going to get a negative value because our datum was below the mean. So minus 1.86. So the question becomes, which of these values is more extreme? Is 2.69 standard deviations above the mean further from the mean than negative 1.86 standard deviations? Yes, because this value is more than 2 standard deviations above the mean, whereas this value is less than 2 standard deviations below the mean. So we could say a man with a body fat percentage of 40.1 is more extreme, or his body fat percentages, than a man with a body fat percentage of 3.7. This part of the worksheet is an opportunity for you to become familiar with the shape of histograms and eyeballing those histograms to estimate the mean and the standard deviation. So as I'm looking at this, I'm seeing that I have a curve that probably looks something like this. Okay. So somewhere there in the middle will be the mean. And then I can take a look and try to calculate what 95% of the data would be above and below that mean. So in this case, about 68 here. Okay. And then where is 95% of this data located? Well, I think when we did this in class the other day, we captured about 75% of the data. So I'm going to be a little more extreme here because it's very important. 95% of the data is almost everything. So we need to make sure we include almost everything. The thing is, our standard deviations are always symmetric above and below the mean. So 2 standard deviations above the mean should be just as far and no further than 2 standard deviations below the mean. So as I'm looking at this now, I'm thinking it's more like 60 here, and that side's pretty easy to see. We have some extremes out here that make it a little bit harder to judge on the right-hand side. So I'm going to judge the left first, and then I'm going to make the right-hand side correspond to that. I said here that, here, 2 standard deviations was about equal to 8. So I should have 8 over here, 2 standard deviations. So I'm looking at about 76 and about 60. Now this is a little bit skewed, so it's not quite looking exactly the same, but I'm thinking that's a pretty good estimate. If I go out further on this side to account for things, I'm very quickly going to completely fall off the graph over here, the absolute value of it. So our standard deviation would be 4. Now, why is that important? Well, let's take a look at some z-scores then. Okay, here's definitely an extreme. And since these are frequencies up the side, it looks like that is one person, and that one person has the maximum height. And I'm looking at this, I'm saying that's about 84 inches. And let's find and interpret a z-score for this person's height. We're going to use the same formula we used before because the formula for z-score does not change. The only thing that might change is whether you are using or computing a z-score for a population or for a sample, as we're doing here. And these are both considered samples. We don't have data for every single man in the world or person in the world. These are students. Okay, every student in the world. Let me move over here so I have some room. There's my z-score formula. Okay, let's calculate the z-score for this height, for 84. So that's going to be the datum of interest, 84, minus our mean, which was 68. And we are dividing that by our standard deviation, not 2 standard deviations, but by 1 standard deviation, which we're estimating as 4. Oops. And when we calculate that, we get a value of 3.75. So let's see. If I draw in the rest of these, let me get out of my equation here. So let me do that. Okay, that was 2 standard deviations. That means 1 standard deviation would be about here. Oops, about there. Okay, and if that's 1 standard deviation, here's 2 standard deviations. 3 standard deviations should be 4 beyond that, so about here. And 4 standard deviations should be about 1, 2, 3, about here. And yeah, that 84 is between 3 and 4 standard deviations above the mean, and it's pretty close to 4. So 3.75 is the z-score for this man who has a height of 84 inches. Now, we don't usually think about it in inches, do we? But that's 7 feet. So yeah, he's pretty tall, okay? Extremely tall. So 1, 2, 3 standard deviations, 3.75 standard deviations above the mean. Okay, we're going to revisit the data given for tips for a pizza girl using technology to find the 5-number summary. So I do not have the pizza girl entered in Minitab yet. So I am going to pull up my pizza girl values. Please use your worksheet to do the same thing. I'm going to go in here under tips, which is the column header. I'm going to go ahead and put in the units too. So I think that's very important. And once again, I'm going to try to do this without making an error this time. 2, 4, 6. Now that I have those in place, I can still do descriptive statistics. I can choose tips. I can find the mean and the standard deviation. Okay, and those do match the values we got from StatKey. But this is asking for the 5-number summary. Now my 5-number summary is in there. It's just this part of it. So let's be specific. I'm trying to communicate the 5-number summary. So I'm going to go to my statistics and I'm going to get rid of everything not included in the 5-number summary. The only things that are included are the minimum, the first quartile, the median, the third quartile, and the maximum. So when I click OK and OK again, here are my descriptive statistics. So I can put that into my worksheet. Here we go. Use technology to find the 5-number summary for the pizza girl's tips. And I need to get out of my draw function and insert. Okay. The minimum value for tips that she received was 0. 25% of the data, 25% of her tips were $2 or less. 50% of her tips were $3 or less. 75% of her tips were $3.75 or less. And the maximum amount of tips she received was $8. If you ask me, the people in this area are kind of cheapskates. All right, so what's the range here? Well, the range is from the minimum value to the maximum value. So we're not giving the interval like we were when we were citing 2 standard deviations above and below the mean. What we want here is a number, and that number is 8. How do we get that? We did the max with an x minus the minimum. That was 8 minus 0 equals 8. So this is our answer. Now, what are the units on this? It's dollars. So let's put it here as our answer with the correct units. So $8. There we go. That is the range. And here's how we calculated the range. What is the IQR? Now remember, IQR stands for the interquartile range. So between the third quartile and the first quartile, that is our interquartile range. So we're going to take Q3 minus Q1. And that's going to equal 3.75, $3.75 minus $2. And that's going to equal, and here I'm going to go ahead and put the units in, $1.75. That is the interquartile range. Most of her tips ranged between $2 and $3.75. If one of the pizza delivery customers had given a $20 tip, which measure of spread would the large tip have a greater effect on? The range or the IQR? There are our descriptive statistics. Watch what you can do with Minitab. Basic statistics, displayed descriptive statistics. Which ones? I'm going to leave the 5-number summary there, but I'm also going to add to this the range here and the interquartile range. Okay, and first I'm going to display this with the data that I have right now. Okay, the range is 8. The interquartile range is $1.75. But if I add down here a tip of $20, what's going to happen? Displaying them again. When I added that $20, the range went from $8 to $20. The interquartile range only went from $1.75 to $2.25. So that's a difference of 50 cents. Which of those two statistics did the extreme value affect the most? The range, much more than the interquartile range. Okay, so I would say something here like the range was affected more because the range went from $8 to $20. And yes, details. Give me details. Let me know what you're thinking. While the IQR only increased 50 cents. And by the way, here's how you can write 50 cents with a dollar sign, remember? Let's take a look at what it was again. 175 to 225. Example 4, percentiles of SAT scores. A score of 400 on the SAT Mathematics General Test is at the 16th percentile for all 2012 college-bound seniors taking the SAT. Clearly explain in terms of SAT scores what it means to be at the 16th percentile. That means SAT scores should show up in the sentence you're using to describe this. Okay. So we could say 16% of all what scores? SAT, mathematics, general test, not all SAT scores combined. No English in this, just looking at the SAT, mathematics, general test. Okay, so 16% of all SAT, mathematics, general test scores were lower than 400. Oh, but wait, what year was this? General test scores in 2012, because the percentiles change every year. Okay. And if you're in a Word document, you can always cut and paste. Otherwise, if you are composing on your own, make sure you get details in your answer. Okay, let's look at this quick self-quiz, 5-number summary and skewness, heights revisited. Okay, we looked at the histogram of the heights of 355 students. We need a rough estimate of the 5-number summary of the heights in this sample. Okay, so let's go back up, take a look at that histogram for heights. Okay, here's the histogram. Watch what happens if I copy it and paste it. And we got rid of all that messiness I had drawn on it. Okay, 5-number summary. We already identified the mean here as 68. Okay, and we said 95% of the data was between here and here. Now that's 95%. That's not what we want. But where is half of the data? Where does that look like? I'm looking at, maybe here. And should be, well, it's a little bit skewed. So, could be out here a little further. Because when we're talking about a 5-number summary, it does not have to be symmetric. So I'm going to say about 63 for Q1. Here's the median. And here's Q3. Okay, so a 5-number summary here. I'd say I'm looking at about, let's see, below 60. I'm looking at about 57, maybe. 63, 68, 70. Let's do about 74. And then the tallest gentleman was 84. So there we go. 57, 63, 68, 74, 84. That is my approximation. Now, could you get different numbers? Absolutely. We're just eyeballing it, right? If we had the original data, we could enter it in StatKey. We could enter it in Minitab, and it would spit out the numbers. Or I could give you all of that data and have you calculate it by hand, which you could do because you know how to find the median, and you might come up with these numbers or something slightly similar. If you're within, say, 2 inches on each of those, it's fine. Even this 3-inch difference, not a big deal, okay? Because we're just eyeballing it. If I ask you to calculate it, either by hand with StatKey or with Minitab, I would want you to get the correct answers. But these are estimates, so you're okay being a little bit off. Okay, and then the next thing we're going to do, I'm going to pull it down a little further, is to look at each 5-number summary below. And let's talk about whether it appears to be symmetric, skewed to the right, or skewed to the left. Okay, this is our 5-number summary, and I'm going to increase the distance here a little bit between them. Okay, I have increased the distance between each of the values, the minimum, the first quartile, the median, the third quartile, and the maximum, because down here below them, I'm just going to calculate the difference between each of these. So between 10 and 57, we have a difference of 47. Between 57 and 85, we have a difference of 28. And between 85 and 88, we have a difference of 3. Between 88 and 95, we have a difference of 5. Where is the larger, or where are the larger differences? They are to the left, aren't they? So this data is skewed left. All right, what about B? Don't really need to do this, do I? Separate them, because look, 200 to 300 is a difference of 100, 300 to 400, 100, 400 to 500. All of these differences are 100. So since all of the differences between each portion of this 5-number summary are 100, then we say that that is symmetric, okay? Because on the left, we have differences of 100, left being to the left of the median, and to the right, we have differences of 100. That's symmetric. And let's go ahead and write that in, because we were asked whether it was symmetric, skewed, or skewed. So this one would be skewed left. This 5-number summary makes the data appear to be symmetric. Okay, what about this set of data? Now here is the median. It falls right here. To the left, we have 10, then 25 as our differences. And to the right, we have 10 and 25. It is symmetric. So the differences between each part of that 5-number summary do not have to be the same in order for the distribution to be symmetric, but the differences do have to be symmetric. There are the differences. They are not symmetric about the mean. Especially here to the right, that's a really big difference. 42 is very far. The maximum is very far from the third quartile. So this one is skewed right. And do you have to separate these on your paper? No, you don't. I'm just doing it to make it easier for me to communicate what I'm doing to you. What are the differences? Is it symmetric, skewed left, or skewed right? Okay, there are your answers for the final one. This distribution is skewed left. Now, I just asked you previously to give me lots of information, right, in detail. If you separate these numbers like this and show me the differences, if I can see that you are calculating the differences and have written that down, and then if you just tell me it's skewed right or skewed left, I can understand that, and I know that you understand it. If we were looking at a histogram, you could say something is skewed right because the tail points right, okay? But here we are, 5-number summary, skewed left, skewed right, or symmetric. And that is the end of that lesson. Now, I do intend to make a worksheet for you to give you lots of practice with eyeballing standard distributions, because that's a difficult skill that you'll need to have in this class. I want to give you time to practice it. And that concludes this video. Please, as always, let me know if you have questions.